Good afternoon everyone, and welcome to today's worked exam answer video. Today I'm having a look at a halogens and halide ion question which covers the knowledge from the group 7 inorganic topic, which is a part of the year 12 or the AS AQA specification. Now I've chosen this question because it covers electronegativity as well as the reactions of different halide ions with sulfuric acid, and part B is worded slightly differently to how it's been worded in the past, and then part C is quite a common skill set and also brings in our redox skills as well. So trying to cover as many different aspects of the group 7 content as I possibly could in one question. So to start off, we're thinking about electronegativity of the halogens, and we have to explain why the electronegativity of the halogens decreases as we go down the group. So this also brings in some structure and bonding knowledge, because we need to know what is meant by electronegativity. So it's good to know the definitions for terms like electronegativity so that we can kind of go, right, okay, first of all, what do we mean by electronegativity? So it's the ability of an atom to withdraw a pair of electrons towards itself in a covalent bond. So when two atoms are sharing a pair of electrons, which one can pull that shared pair of electrons closer to itself? And then we can think about what happens in this case as we go down the group with the halogens. So going from fluorine at the top, fluorine, chlorine, bromine, iodine, what happens to the halogens? They get bigger, as do all atoms as we go down a group, because we've got more electrons, so we've got more main energy levels, more electron shells, and that means the outer electrons are going to be further from the nucleus. And if that is the case, if an iodine atom is sharing an electron with a hydrogen atom, for example, to get that covalent bond, the shared pair of electrons is going to be quite a long way away from iodine's nucleus, whereas if we change the iodine for fluorine, because fluorine's a lot smaller, the shared pair of electrons between a hydrogen and fluorine atom are going to be sitting very close to fluorine, and that's because fluorine's nucleus can more strongly attract the shared pair. So we've got to know what we mean by electronegativity, and then we've got to think about what is happening to the halogens down the group, and then we should, if we know both of those things, be able to pair those together. So I'm going to say that the halogen atoms get larger as we descend the group, and therefore the elements will form weaker attractions to the shared pair of electrons in a covalent bond. So it's going to want you for your 2 marks to talk about the change in the size of the atoms and the change then in the attraction of the nuclei of those atoms, which I was just thinking I haven't mentioned, and therefore the elements will form weaker attractions to the shared pair of electrons in a covalent bond. And therefore the elements will form weaker attractions to the shared pair of electrons in a covalent bond. I'm going to change that. between its nucleus get rid of that. So, and therefore the elements will form weaker attractions between its nucleus and the shared pair of electrons in a covalent bond. So stating what the attractions are between, I felt it was important to get nucleus in there. So yeah, 1 mark for change in size, 1 mark for how that affects the ability to attract. So weaker attractions will be formed when the atoms are bigger, stronger attractions will be formed when the atoms are smaller. Okay. Then we're going on to have a look at how the halide ions react with concentrated sulfuric acid. So this isn't a required practical, but it is one that gets talked about a lot. So the difference here is that we've got a chloride ion and we've got a bromide ion. And we have to state one similarity in the reaction between sodium chloride and sodium bromide with sulfuric acid, and then one difference between those two reactions as well. So all of the halide ions will react with sulfuric acid in an acid-base reaction, where the sulfuric acid will give up a proton and we would then get sodium hydrogen sulfate being formed, and the halide ion would react with the H+ that the sulfuric acid donates, and then that would give us our hydrogen halide. That will happen with chloride ions, bromide ions and iodide ions. So that's going to be my similarity. Acid, base, reaction to form NaHSO4 and HCl/HBr. That would also happen for the sodium iodide, so the iodide ions would behave in the exact same way. So that is your similarity in those two, that's the similarity when we have chloride and bromide ions. If we were thinking about bromide and iodide ions, a similarity could be the amount of reduction that the sulfur and the sulfuric acid undergoes. Both bromide ions and iodide ions can form SO2 as one of the products, so that could be a different similarity we could use with the bromide and iodide ions. Then we've got to think about a difference, and the difference is going to come from the ability of the bromide ions to reduce the sulfur in the sulfuric acid from +6 down to +4, which is what it is in SO2. The chloride ions can't bring about any reduction at all. So this practical is thinking about the reducing ability of the halide ions, and the chloride ion is a terrible reducing agent to the point where no oxidation and reduction occur if we have the chloride ion being used. Some reduction occurs when we use the bromide ions. More reduction occurs when we use the iodide ions. So we need to be aware of the trend in reducing ability down group 7. And for me, this comes back to telling ourselves the story of a reducing agent reduces something else and is itself oxidized. Oxidation can be defined as the loss of electrons. So we're thinking about how easily will a chloride ion or a bromide ion or an iodide ion give up an electron. The bigger the ion, the easier an electron can be lost, because again it comes down to the attraction between the nucleus and the outer electron, which would be the one to leave the ion to turn it back into an atom. And because chlorine is much smaller, the chloride ion isn't going to want to give up an electron. It's not going to be an easy thing for it to do because it's being held, the outer electron, by the nucleus so strongly. So it makes sense that the iodide ions can be oxidized most easily and therefore act as the best reducing agents. So for this particular question, no redox occurs at all with the chloride ions, but with the bromide ions we do get redox. So that's what I need to say. So no redox reaction with NaCl, but with NaBr, the Br minus ions will be oxidized to Br2 whilst the sulfuric acid is reduced to SO2. So quite a major difference there in terms of, again, thinking about comparing sodium bromide and sodium iodide. It would be the extent to which the sulfuric acid could be reduced. So in the next question, we get told that solid sodium iodide reacts with concentrated sulfuric acid to form hydrogen sulfide. Bromide ions can't do that. Similarly, iodide ions can reduce the sulfuric acid down to pure elemental sulfur. Again, bromide ions can't do that. And when we're thinking about oxidation states, the sulfur in sulfuric acid is +6, in SO2 it's +4, in elemental sulfur it's 0, and in here, in hydrogen sulfide, it's actually -2. And that is the lowest that sulfur's oxidation state can be, and the iodide ions can reduce the sulfur all the way to its lowest oxidation state. So that proves that they get better reducing agents as you go down the group. So this question is going to be getting us to think about writing an overall redox equation for the reaction between the iodide ions and the concentrated sulfuric acid to form this hydrogen sulfide. So we've got to have an oxidation half equation, we've got to have a reduction half equation, and then we're going to combine those together. Now, it hasn't used the word redox in the final part of this question, but a redox equation is what we are going to be writing. Half equations are those which include electrons, and then when we join those half equations together, we shouldn't have electrons in there anymore. So we've got oxidation of iodide ions, the reduction of concentrated sulfuric acid to hydrogen sulfide, and then we've got to combine those together to deduce the overall equation, which would be redox for this reaction. So, iodide ions, I-. Oxidation is loss of electrons. So if the iodide ion loses an electron, it will become an iodine atom. And it will have lost an electron, so we can put that there like that. Now, because iodine is diatomic, we would actually need to be forming I2 molecules. So we'd need to start with 2 iodide ions that could each give up 1 electron. So a total of 2 electrons would be lost, and then once we've formed those 2 iodine atoms, they would join together to give us our iodine molecule. Oxidation is loss, so the electrons should be on the right hand side, or we could also have a think about the oxidation states. So oxidation is represented by an increase in oxidation state, so -1 for the iodide ions, because it's an element here, that's 0. -1 to 0, increase in oxidation state. So I know I've got my electrons on the right side. And if you're ever unsure about the electrons, using your oxidation states can be helpful. Anytime we've got electrons that need to be lost, they should be on the right hand side. Anytime we're doing reduction, the electrons should be on the left hand side. We should have the same charge on both sides of our equation. So 2 negatives here, 2 negatives here. And that was slightly easier because we only had to balance that with electrons, whereas this time we're starting with our sulfuric acid, H2SO4, and we're trying to write an equation to show the reduction of that to H2S. Now, we can't just balance this with electrons because we then wouldn't have a balanced equation, and we've got to have a balanced equation in terms of numbers of atoms and charges. So first step is to check that everything that isn't hydrogen and oxygen is balanced, in this case our sulfur. Yes, it is. Then we balance the oxygens, and we do so by adding water to the appropriate side, so 4H2O. So that's got 4 oxygens on the left, we've now got 4 oxygens on the right, but I've now got a total of 8 plus 2 is 10 H's on the right and only 2 on the left. And we balance our hydrogens by adding H plus ions, which would come from an acid. And then we need to balance our charges. So I've got no charge on the right hand side because these are both neutral compounds. And so to balance out the 8 positives, I'm going to need 8 electrons here. Reduction is gain, electrons are on the left. Awesome. Sulfur is going from +6 down to -2, decrease in oxidation state, reduction. Excellent. And now, combining those together, before we can just join the equations together, the electrons have to be balanced. And that's because if these iodide ions can only lose 2 electrons in the formation of one iodine molecule, and the sulfuric acid needs to gain 8, where are the other 6 coming from? Because the electrons can't just be generated from thin air. So we've got to have the oxidation reaction giving us the number of electrons we then need in the reduction reaction. So we need to have more of the iodide ions. So we're going to multiply everything in this equation by 4 so that we then create 8 electrons, which can then be gained. And we should not have any electrons in our overall equation. So once I write everything that's on the left and the right, I'm going to ignore the electrons. So timesing 2i minus by 4 gives me 8i minus. And that's everything from the left-hand side of the top equation. Then I'm going to add everything from the left-hand side of the bottom equation that isn't the electrons, because they will cancel. So that's me done. And then on the right-hand side, I'm going to now have 4 lots of I2. Not interested in the electrons because that would be 8, and I've got 8 on the left, so they would cancel. And then from the bottom equation, I've also got my H2S and my 4H2O. And that is my overall equation to show how oxidation and reduction occur at the same time to give us this lovely redox reaction here, in which the sulfur is reduced to its lowest oxidation state. If anybody has any questions, please do not hesitate to let me know. In organic chemistry, there is a lot of learning that we need to do. So with these reactions, knowing what products, what types of reactions we get is really important, and also being able to explain the trends. And that's important in terms of a learning point of view, that we know what we mean by things like electronegativity in this case. They could have asked us the first ionization energy and how that changes down the group, and again that would then be thinking about making sure we know the definition for first ionization energy as well. So quite a lot of stuff being tested there. As I said, any questions, please let me know. Hope you all have a fabulous day.